Hey everyone, and welcome to This Explainer. Have you ever just paused for a second and wondered how a simple text message, a photo, or even the video you're streaming right now actually travels invisibly through the air to reach your device? We completely take it for granted, but the physical reality of how data actually moves across networks is, frankly, nothing short of invisible magic. So today, we're going to pull back the curtain on the physical layer of computer networks, and we're going to focus specifically on the wild, totally unpredictable world of wireless transmission.
Okay, let's look at our roadmap. We'll be covering 5 sections. First, data to digital signals. Second, obstacles, which are the transmission impairments. Third, sharing the channel through multiplexing. Fourth, the power of OFDM. And finally, advanced wireless techniques like CDMA and MIMO. Let's dive right in.
So how does a simple 1 or 0 actually survive a chaotic wireless journey? I really want you to keep this question in mind as we go. Think of a single digital bit, just a 1 or a 0, as this tiny, incredibly brave protagonist embarking on an epic, highly perilous journey through the airwaves. I mean, it's leaving the total safety of a copper wire and getting blasted out into an environment packed with interference, physical walls, and even weather. How in the world does it survive intact?
Let's start with Section 1, Data to Digital Signals, Preparing for the Journey.
Before our little data bit can even dream of traveling through the air, it has to be properly packed up and prepared for the specific medium it's about to enter. Engineers use a very precise 3-step sequence for this. First up is source coding, which compresses the raw information. Next, we have channel coding, which adds crucial protection to the data. And finally, modulation. This converts the coded data into a physical signal, like a continuous time waveform that can actually physically travel over the medium. A key takeaway here is the difference in priorities based on the medium. See, a wired link is relatively safe, right? So the physical layer there focuses almost entirely on just maximizing speed and throughput. But a wireless medium? That's exposed to the public, and it's incredibly hostile. So the preparation phase heavily prioritizes protecting our protagonist bit from getting corrupted.
Now you might be wondering, why do we convert this to a digital signal in the first place? Well, analog signals are continuous waves, which makes them really easily and permanently distorted by random noise. Digital signals, on the other hand, use discrete values. And this gives our protagonist bit a real fighting chance. Why? Because as a digital signal degrades over distance, repeaters can step in and perfectly regenerate a brand new, pristine 1 or 0. When you combine that with error-correcting codes, digital absolutely becomes the gold standard for modern networks.
Which brings us to Section 2, Obstacles, the Transmission Impairments, or, as I like to call them, the Antagonists of the Airwaves.
Once our perfectly prepared digital signal actually leaves the antenna, the laws of physics immediately step in and try to destroy it. Our very first villain here is attenuation. Put simply, this is our brave signal just running out of energy as it travels. It's exactly like how a yell turns into a whisper across a large field. Electromagnetic waves lose intensity due to the resistance of the medium. They get absorbed by water particles, or they scatter. In radio transmission, the signal drops by a massive fraction every single time the distance doubles. So to combat this, engineers literally have to place low-noise amplifiers at the receiver ends just to boost the signal enough to figure out what the original message even was.
Then we have noise, and we're not just talking about someone talking loudly. In networking, noise is this chaotic background fluctuation that is constantly interfering with our signal. It could literally be thermal noise generated by the heat of the electronic circuits themselves, or maybe impulse noise from a sudden lightning strike or a nearby power line. This ambient background noise is actually the fundamental reason why our wireless speeds are limited. It forces engineers to make a tough choice, either crank up the transmission power or slow down the bit rate just so the receiver can actually tell our protagonist bit apart from the surrounding noise. And finally, we meet the final boss of wireless antagonists, multipath fading. See, when a signal is broadcast, it doesn't just travel in a perfect straight line. No way. It bounces off buildings, the ground, cars, the atmosphere, everything. This means the receiver isn't just getting one clean, crisp signal. It's getting dozens of echoes, and they are all arriving at slightly different times. And because they're out of sync, these echoes quite literally collide with each other, causing destructive interference that threatens to just completely wipe out our data.
Let's put this into perspective. A signal can travel directly along the surface of the Earth as a ground wave, right? But another portion of that exact same broadcast is shot upward, bouncing off the ionosphere before coming back down. Because that bounce signal travels a much longer distance, it arrives late.
Imagine trying to listen to someone speak but hearing a slightly delayed, equally loud echo of their voice at the exact same time. It makes the receiver's job of piecing those original ones and zeros back together incredibly difficult.
Section 3. Sharing the channel, multiplexing, the engineering solutions.
So, physics is tough, clearly. But engineers are incredibly clever. How do we not only rescue our little bit from these obstacles, but also allow thousands of different users to share the exact same physical airwaves without stepping all over each other? Well, the foundational answers are TDM and FDM. Let's use a highway analogy here. TDM, or time division multiplexing, is like cars taking turns going through a single-lane tunnel. Every user gets the entire bandwidth, but only for a tiny recurrent fraction of a second. They take turns really rapidly. FDM, or frequency division multiplexing, is an entirely different approach. It's like paving a massive highway and drawing lines to create separate, dedicated lanes. In this case, each user gets their own frequency range, operating continuously without overlapping into someone else's lane.
And you actually interact with both of these every single day. TDM is heavily used in digital applications. Think traditional telephone architecture and cellular networks, where your voice data is chopped up into those tiny time slots. FDM, on the other hand, takes advantage of analog passband transmission, and it's the exact technology behind AM and FM radio. So when you tune your car radio to 98.1 FM, you are quite literally selecting one specific frequency lane that the FCC has isolated from all the others just to prevent interference.
Section 4. The power of OFDM, packing data tightly.
As our demand for speed grew, those traditional lanes just weren't enough. This brings us to OFDM, an advanced evolution of frequency division that completely revolutionized wireless networking, especially when it comes to early Wi-Fi. OFDM stands for Orthogonal Frequency Division Multiplexing. Normally, if you pack frequency lanes too close together, they bleed into each other and create crosstalk. So you usually need wasted empty space, which we call guard bands, between them. But OFDM uses some absolutely brilliant mathematics. It divides the channel into tightly packed subcarriers that are orthogonal. And because of this exact mathematical relationship, the peak of one subcarrier lines up perfectly with the 0 point of the next one. This means they can overlap tightly without interfering with one another at all.
The impact of OFDM is massive. By splitting a fast data stream into many slower, parallel subchannels, OFDM effectively neutralizes our old nemesis, multipath fading. If an echo delays a tiny piece of the signal now, it doesn't wreck the whole stream. This genius technique eliminated intersymbol interference and is exactly what boosted our old 802.1a and G Wi-Fi standards all the way up to 54 megabits per second. The only catch here is that it requires incredibly accurate frequency synchronization between the transmitter and receiver to maintain that perfect mathematical harmony.
Section 5. Advanced Wireless, CDMA and MIMO, the climax of signal survival. Now we reach the absolute cutting edge. This is where engineers got wildly creative with the physical properties of radio waves. First up is CDMA, or Code Division Multiple Access. Remember our highway analogy? TDM takes turns, FDM uses separate lanes. Well, CDMA throws the highway concept completely out of the window. It is a spread spectrum technique where everyone transmits at the exact same time using the entire frequency band. So how is it not just pure static? Well, every user's data is mathematically multiplied by a unique, high-speed digital code, a pseudo-random noise sequence. To anyone else, your signal literally looks like harmless background noise. But your specific receiver, which is equipped with the matching code, can filter out the entire room and perfectly reconstruct your protagonist bit.
And that brings us to the ultimate game changer, MIMO, or multiple input, multiple output. Standard wireless systems have one antenna talking to one antenna. MIMO uses multiple antennas on both the transmitter and the receiver. By exploiting the actual spatial dimensions of the room, it creates entirely separate, parallel bit streams, a technique known as spatial multiplexing.
And here is the true, absolute genius of MIMO. Remember multipath fading, that devastating phenomenon where bouncing signals crash into each other and destroy our data? MIMO takes those exact, delayed, bouncing echoes, figures out their spatial paths using advanced signal processing, and then uses those bounces as extra parallel channels to push even more data through. It literally turns the very laws of physics that used to break our networks into the exact engine that powers our fastest gigabit speeds today. It's just incredible. From struggling to get a single bit through the noise, to weaponizing the room's echoes to multiply our bandwidth, the physical layer is just a massive testament to human ingenuity. which leaves us with this provocative thought. With technologies like MIMO literally turning the most frustrating laws of physics to our advantage, what seemingly impossible barriers will the physical layer break next? Thank you so much for joining me on this explainer. Keep wondering, keep learning, and I'll catch you next time.